Yes, and the integration constant, or we just
It doesn't matter in this case because
yeah.
like for integral constants, like it's a differential equation that never appears s only. S on appears through a derivative only, so additive constant doesn't make any difference. So you can add something, but that's the same thing. So that's why in Hamilton Jacobi you never write the integral constant here. You need not to. We can write like that. Also, by analyzing the other part, we can see that the only x dependence is here, right?
Yes.
The other part is not x dependent thing. So ds x over dx, it has to be some constant as well.
Yeah.
Say alpha. And it automatically gives us sx equals to alpha x. Same
Yes.
thing is for the y part as well.
Yeah.
So dsy over dy equals to some beta.
Yeah.
Equals to, it gives you sy equals to beta y. But for the z is different. So
It is
substitute constant. Yeah, substitute all of those. So we are having 1 over twice m, then alpha squared plus beta squared plus dsz over dz whole squared plus mgz minus minus e equals to 0. So you could choose this thing as positive a as well, but we know this is st part is like if you consider negative e, so that will give you like e has a meaning now. It is the energy of the system. So that's why for the time part we always write it as negative something. You could do the positive one as well, but it doesn't make any difference.
Yeah. Okay.
So now,
Why this dsx by dx is equals to alpha? A constant?
yeah, because the only x dependence is here. So this term is only y dependent. This term is only z dependent, right?
Yeah, yeah.
So if you change your x a little bit, say your dsx over dx, it can only depend on x because by definition, sx is a function of x only, right?
Yes.
So if this part depends on x explicitly, then if you change your x a little bit, then this dx over dsx over dx changes, but the other part still remains same. So the only possibility we are left with, that is alpha has to be a constant. Like dsx over dx has to be a constant.
Okay.
So substitute all of those. We are finally we're having this relation. That is, just simplify it. It gives you dsz over dz whole squared equals to e. Sorry, how do I write it? Okay. Twice m multiplied by e minus mgz minus alpha square minus beta square, right? Doing the algebra.
Yes.
So we have dsz over dz equals to square root of twice me minus mgz minus alpha square minus beta square. Actually, alpha square, beta square, and twice me, all of those are constants, so we could dump into just one single thing. That would be more productive, but okay for now. So sz is integration of square root of twice me minus alpha square minus beta square minus twice m square gz, right? So what would be the integration of this thing? I think it's a simple integration. You can do some change of variable and find something.
Yeah.
Yes.
So how do we do it?
I can write something else instead of this whole term, a new variable. I can define a new variable. For
Okay.
example, p equal to this constant minus the z terms.
So let's define 2m squared gz equals to u, right? That would work, I believe.
Yes.
So that gives me 2m squared g dz equals to du, which means dz equals to du divided by twice m squared g.
Yes.
So now we have sz equals to integration square root of this is let's call it big A. So A we'll substitute that later actually. A minus u, then du divided by twice m squared g. So what's that? So it will give us a minus u whole to the power 3 by 2, then divided by
By I just proposed a different thing. The whole terms, the constant a minus the z terms will be a new variable. I can define.
I have done it already, right?
Oh, okay.
So yeah, I know what you mean. So you meant actually instead of this, actually you meant this thing. Instead of defining that, you wanted to define 2me minus alpha square minus beta square minus twice m square gz equals to u. That's what you wanted to do, right?
Yeah.
So then your inside of this square root, you just have u, and then here you have again negative twice m square g dz equals to du, right? So dz equals to negative u of that thing. So instead of having like in your transformation, I'll have this square root u du divided by negative 2 m square g. This is what you wanted to do, right?
Yes.
Yeah, that's the same thing. That's what I did as well. So it gives you u to the power 3 by 2, then divided by 3 by 2 means 2/3, right? And then you have your 1 over negative 2m square g. So now substitute everything back. So these two cancel out, and you have negative u to the power 3 by 2 divided by 3m square g. And what is your u? U is that whole thing, right? U is your 2me minus alpha square minus beta square minus 2m square gz all to the power. So this is your sz, right? I believe this is what you wanted to do, right?
Yes.
So we have collected all. Now we need to collect all the pieces of S. So S as a function of x, y, z, and t. What would be that?
It is alpha.
What was the ansatz? Ansatz was sx
Sx plus
st of t. St of t. What is st of t? St of t. Negative.
Negativity. Negative.
Yes. So negative et.
Yeah.
Let's write it down. Oops. We cannot go. behave
Yeah.
sometimes really weirdly. Okay, negative et.
Yes.
This is your st of t.
Yes, then হচ্ছে plus alpha x.
Then sx you need to
Yes.
write. So alpha x, then
And sy equal to হচ্ছে beta y. So equal to beta y. Then sz equal to
s equals to negative
negative, the big term,
1/3 m square g, 1/3 m square g multiplied by twice me minus alpha square minus beta square minus 2 m square g z whole to the power 3/2.
yes.
Okay, we can do a little bit change here. So this whole thing is a constant, right? And some unknown constants. We can keep it like that. Also, we can simplify it as well. That's what I mean. So can we consider this thing to be like gamma squared?
Okay.
So if this thing is gamma squared equals to twice me minus alpha square minus beta square. So it gives me alpha square plus gamma square plus beta square equals to twice me, right? So what's my e? E equals to 1/twice m alpha square plus gamma square plus beta square. I can write like that. Just renaming those variables, renaming those constants. I can do that. So I can write, I can write like this: negative, what is e? E is 1/twice m, and then you have your, on the top you have alpha square plus beta square plus gamma squared into t. Happy?
Yes.
And then you have plus alpha x plus beta y minus instead of this whole thing you have just gamma square over there, right? So 1/3 m square g, then you have gamma square minus twice m square g z whole to the power 3/2, like that. Do you agree? So this is the solution for our s in terms of 3. Like we expect s to be a function of we expect our s to be a function of q, big Q and t. So yeah, it's an explicit function of big T, small t, and also it's an explicit function of all the coordinates like x, y, and z. So what are those Q's?
Alpha, beta, gamma.
Yes. Any constant that appears from separation, that's your big Q's.
Yes.
So so this is our solution. So what do we do with that? Like, is this the final solution that we wanted? So we have solved our s. Now what? Any idea? So see which equations we have used already. So we have used h plus delta s by delta t equals to 0. That's we have used. Also we have used delta s by delta qk equals to pk. That's what we have used.
Yes.
So
And
is there any equation that's left?
the last equation, delta s by delta capital qk. because
delta S by delta capital QK equals to
and it will be our negative pk or
this thing we haven't used. So if you take derivative of S with respect to those constant parameters,
yeah.
then you'll have new constant parameters. That's what it means.
Yeah.
So it means now you have to take this thing, delta S by delta alpha, and you have to set it with, you have to equate with something else that's also constant, say big alpha, like that. Because we know already by construction that pk and qk are constants. Big pk
Yes.
and big qk are constants. So now take derivative. So what do you get if you take delta S by delta alpha? Tell me.
I will get alpha by m in times minus alpha, so minus alpha.
Negative alpha by mt, that's from this part, right?
Yes,
plus
And then
x.
plus x.
plus x.
Yeah.
So this is
Oh.
my final equation. That's my
Oh.
final I wanted to find. So invert your x now. Your x as a function of time is now
A constant a plus
no,
a
negative a, right? We got
yes,
negative a
yes, negative a plus alpha by
plus
m times t.
alpha by m into t.
Yes. Yes.
Isn't that neat? Okay. So what happens when we take derivative with respect to beta and set it to be something else, something to be constant?
We will get the similar equations as we get for alpha.
Let's set it to be big beta. So
Okay.
yes.
Minus
So then
beta by m times
negative beta by m
times
t
t. Yes.
plus
y.
Plus y. So it gives you y as a function of time to be negative beta plus beta, small beta by m into t.
Yeah. Yes.
Also, you have your final piece, that is delta S by delta gamma. Let's say it gives you big gamma. That's equals to, what's that? That's a little bit tricky, I believe.
Yes. It's the first term will be similar like
Again, negative gamma by mt. Then
then minus 2 gamma.
is it minus 2 gamma?
Yes.
No. It will give you something complicated. So you have to take
Yes.
derivative here.
Yeah, so
So it gives you negative 1 over 3 m square g. Let's write that down. Then your power goes down 3 by 2 gamma square minus twice m square g z whole to the power half. Then you have to take that derivative, so twice gamma, right?
Yes.
Now you invert this thing and find the solution for z. So what do you do here? How do you invert this thing? You have to find z here. So do the simpler calculation. Like, so this thing cancel out, and these two cancel out, right? So you have your gamma equals to small gamma by mt, right? Small gamma by mt, then plus small gamma divided by m square g into gamma square minus 2 m square g z whole to the power half. Now you invert all of those things. So it gives you gamma minus small gamma by mt, that's multiplied by m square g divided by small gamma, then this thing whole squared. This thing gives you what? Gamma square minus m square gz, right?
Yes.
I'm doing the algebra only. Don't get intimidated by this. So then what do? You just take this thing on the other side, that thing on the other side. So it gives you twice m square gz equals to gamma square minus those whole thing, gamma minus gamma by mt into m square g divided by gamma, this thing whole square. And then z of t equals to 1 over twice m square g, I believe, right?
Yes.
And then you have your the other part. So gamma square minus gamma by mt into m square g by gamma. Is this the solution for z, or this thing is
Yes.
just happy?
Yes, it's right, I think.
How do you say that it's right?
Well, the algebra is right, actually. Algebra is all right, I said.
Okay, so is this the formula for z? Like right formula, or expected formula for z, or not? That's what I'm asking. So all you need to do, you need to simplify it, then you'll see it. So it gives you 1 over twice m square g, that's fine, then gamma squared, and then you have to take this whole square as well. So what do you get from there? So it gives you m to the power 4 g squared divided by gamma squared.
Times.
Yeah, and then times gamma. Actually, I should write in the other way. So I should write this way: small gamma square by m square into t squared, then twice big gamma small gamma by mt plus gamma squared, right? This is the whole square thing.
Yes.
Now
Yes.
we are in the position to like compute part by part.
Yeah.
So this gamma square part is just a constant part that adds up with the last one. So we are actually looking for
It will
t to
give.
the power something. Yeah, so t to the power something. So
Yeah.
look for this term. What do you get?
For this term,
Minus sign, that's for sure. So minus
minus g half
that gamma and that gamma cancel out.
Yeah, half gt squared.
Yes, it gives you half gt squared.
Yes.
Do you see it?
Yeah.
For the first term, you get negative half gt squared. Then
then negative.
Then
negative.
is it negative or positive? It's positive because you have minus sign here. So it's positive.
Positive. The two will cancel each other, and m square. There will be m square term.
Yeah, just
M term.
so there will be m term.
M
So
term.
m, then g,
G.
then there will be just
Gamma term. Yeah.
and also there should be a big gamma, right?
Yes. Big gamma times t.
Is that okay?
Yes, I think so.
Did I miss something? Let's check it. Let's check it again and make sure that we did not miss anything. I believe it's fine because that's in the expected form.
Yes.
So, and then finally,
gamma square plus gamma square by 2 m square
small gamma square, right?
Yeah, yes, small gamma square.
Okay, I'm doing the algebra. So here you just multiply. So it gives you a gamma square minus m to the power 4 g square divided by small gamma square into big gamma square divided by twice m square g. That's what you get, which is basically a constant term.
Yes.
So you can simplify if you want to simplify, then you can simplify like this. Okay, so we are almost done actually. Actually, I do not usually bother about like simplifying this kind of thing, because if you just set the initial data, it will automatically vanish many times. Actually, you get gamma to the power 4 minus m to the power 4 g square big gamma square divided by twice m square g gamma squared. So these are three expression we got. So for z we had this, then what we have for x of t, we had negative a plus beta by mt, right? Sorry, alpha by mt, right?
Yes.
And for y we had negative beta t plus small beta by mt. Now still you need to substitute your
minus beta, minus capital B plus beta by mt.
minus capital, sorry. Oh, yes. There shouldn't be a t. That's what you mean, right?
Yeah.
So now this is my solution, but we haven't substitute our initial data, right?
condition. Yes.
Yes. So now we need to substitute our initial data. What was initial data for x?
It is x equal to 0 at time 0.
Yes, it's x equals to 0 at time 0.
Yes.
So x at 0 equals to 0. So if you substitute like here,
It will give a
x
equal
at
to 0.
0, it gives you negative a, because t equals to 0, so it gives you negative a, and that has to be equal to 0. It automatically gives you negative alpha, or alpha equals to 0, right? So by substituting that one, you are reducing down your expression into this x of t equals to alpha by mt, but it's still not enough. You need to substitute the other something as well. So what's that?
It is the velocity.
It's the velocity, initial velocity. So take derivative. So you get x dot t equals to alpha by m. And what was that?
Equal to 0. T
It was
equal to
alpha 0 as well. So x dot at 0 is alpha by m, and that's also 0, gives me alpha equals to 0.
Yes.
So finally, this expression, like expression for x of t, that's the final solution of this thing. After substituting the initial data, this gives me 0. Because there isn't anything left. Big alpha equals to 0, small alpha equal to 0 as well. Now what about y? Y is also y at 0 equals to 0, right? It automatically gives me big beta equals to 0. That reduces down y of t equals to small beta by mt. Now you need to substitute the initial velocity data. So y dot at t equals to just beta by m. And what's that?
Vy.
It's vy naught.
Yeah.
Vy naught. It gives me beta equals to vy naught multiplied by m.
Yes.
Or just beta by m equals to vy naught. So substitute that, you get y at t equals to, that's 0, but that part gives you vy naught multiplied by t. This is expected result, right?
Yes.
Okay, what happens to the z part? So also we know that z at 0 equals to 0. What do you get from that? If
From
you
that, the
the
term,
last
the last
term,
term
this messy term,
will be
it
zero.
gives you
Yes,
0, right?
and it will give me idea about gamma.
Yes, it will give you a relation between small gamma and capital gamma.
And
That's true.
yes.
Actually, we need not to do that, because if now you're reduced down your z of t equals to half gt squared plus mg gamma by small gamma t. So now you need to substitute your velocity data. So z dot at t would be negative gt plus mg gamma by small gamma. And what was that? What was z dot at 0?
Vz naught.
Vz naught. And that gives me equals to mg gamma by small gamma. So I know mg gamma by small gamma is just vz naught. So this part is just vz naught. So I have my final solution, z at t equals to negative half gt squared, then plus vz naught. Isn't that the solution we expect from a projectile motion in 3 dimension for the given initial data?
It is.
Yeah.
Okay, so now do you get like how you need to solve like Hamilton Jacobi?
Yes.
Well, there was a PDA, and there could be other solutions.
Yes, there could be infinitely many solutions, but if one works, that's enough.
Well,
Any solution that works and has enough initial data, like enough constants that you need, then it's fine. So what you are looking, actually, when you're trying to solve like the Hamilton Jacobi for this particular problem, so you're looking for a S that has like x, y, z and t dependence. Also, it has 3 independent constants inside of it. That's what you're looking for. Any solution that has these properties, x, y, z and t explicitly, and also 3 unknown constants explicitly, then that's the solution actually you want, if that satisfies. Doesn't matter how you got that.
yeah, understood.
Okay, I'll take a break for 15 minutes and then I'll come back. How much do you have? I think we can do one more problem, right? Harmonic oscillator or something like that. So Carl, are you following? It's a little bit
Yes.
mathematical, right?
It's mathematical, but I mean it's not inscrutable. It's just it's not a. Let's put it this way. I'm looking forward to when we get to the 4-dimensional stuff. It's much more complicated, right? It looks terrible. I'm joking.
Yes.
That's
yes.
what I'm looking forward to, because those are easier. Well, initially there is.
Yeah. So, Ms. Bajaj,
Yeah, I
were you
am.
able to follow?
Yeah, I am able to follow, but I'm sure that I won't be able to do it myself. I need a lot of practice.
Yes. Hamilton Jacobi requires a lot of practice. It requires a lot of practice. Okay, I'll take 15-minute break, and I'll come back at in my clock it's 11:55 a.m. I'll come back at 12:10 p.m. Hi. Do you guys have any other question so far? We'll do like now we'll compare the formalisms and then we'll solve another problem. That's for today. So far we have four standard formalism of classical mechanics, right?
Yes.
Newtonian mechanics, then Lagrangian mechanics, then Hamiltonian mechanics, sorry. Okay, Hamiltonian mechanics, and then Hamilton-Jacobi theory. So the standard equation of motion for these systems are like F equals to ma for n number of particles. Then Lagrangian mechanics, we already know this is delta L by delta qk equals to ddt of delta L by delta qk dot. Then Hamiltonian mechanics, we have a pair of equations, that is manage it. Okay. Can you guys give me one moment? It's my mom actually calling, so I'll just come back in a moment. Please give me 2 more minutes and I'll
Sure. Sure.
Yes. Okay, so what we were saying here. So okay, so for Hamiltonian mechanics, we have a pair of equations. That is, one of them is definition of momentum. That is delta H by delta pk equals to qk dot, and another is the actual equation of motion, negative delta H by delta qk equals to pk dot. And for Hamilton-Jacobi theory, we have a set of 3 equations actually. So a set of 5 equations, but 2 of them are actually trivial, so we do not write those down. So the other non-trivials are delta S by delta qk equals to pk, that's the definition of momentum. Then H as a function of qpt, actually we all know that, plus delta S by delta t equals to 0. And the final one is delta S by delta big qk equals to negative pk, big pk. So these are our 4 standard formalism of classical mechanics, and as you can see, they have advantages and disadvantages. So let's discuss those things, and we'll proceed to solving another problem in Hamilton-Jacobi theory. So as you can see, how many equations are there? Like how many Newtonian mechanical equations do you have for n number of particles? So you have n vector equations, right? For big n number of particles. So you have n vector equations. Sometimes that's why it's a vector equation, so that's why it's called vectorial mechanics as well. And other 3 are known as analytical mechanics. So for Lagrangian mechanics, how many equations do you have? For 3-dimensional system and with m constraints, you have 3n minus m equations. Here you have 2 into 3n minus m equations.
Yeah.
So how many equations do you have here in Hamilton-Jacobi theory?
3 into 3n.
You're saying 3 into 3n minus m?
No. Oh no. The second equation
So this one is
should
just,
be counted. Yeah.
yes.
So
that,
2 into 3n minus m plus 1.
yes, it's a 2i's into thrice n minus m plus 1 equations here. But this one is actually a partial differential equation. That's what makes things complicated. But other 2 equations are basically transformation equations. So sometimes people say that Hamilton-Jacobi's equation is just one equation that you need to solve. That's true as well, because once you can solve this equation, and you are done actually. The other things are not, you do not need to solve those. You actually substitute and take derivative. For solving, you just need to solve one partial differential equation. So
How did you get that number of equation in the Hamilton-Jacobi theory?
so here, like, you have k means k runs from thrice n minus m, right? M is the number of constraint, and big N is the number of particles. So in
Yes.
3 dimension, so here you have here you have twice. Here you have thrice n minus m. Also here you have thrice n minus m, and also this one.
Okay. Okay, got it.
Yeah. Okay. So now how do you proceed it? There are recipes, right? There are standard recipes that you need to solve this system. So let's write those down. So first step to solve anything using Newton's law, what's that? What's the first step, absolute first step? Set up a coordinate, right? What's the next step? What's the next step? In Newton's law, the biggest,
Finding out the forces.
Yes, find the forces. That's the next step. So find the forces. Find the Fi. That's actually a challenging step sometimes. Okay, then what's the next step?
Writing the equations, vector equations.
Okay. Write down F equal ma, right?
Yes.
And then
Then we
Solving.
can solve it by considering n
resolve
equations.
that equation in that particular coordinate system.
Yes.
Resolve the equation in the chosen coordinate. And the fifth step is solve the generated differential equation. Differential equations. So this fifth step is probably the hardest one, because it doesn't say anything how to solve the differential equation, because mechanics is all about solving differential equations, and it just says like just solve the differential equation. We do not know how to do that. So Newton's law doesn't provide any way or any method automatically to solve a differential equation. So that's the biggest challenge in Newtonian mechanics. So there are two challenges actually. One is finding the force. That's one big challenge, and another is solving the generated differential equation. So now, what are the steps to do the same problem in Lagrangian mechanics? What are the steps?
The first step is transformation of the coordinate system to a generalized coordinate.
No, this is the same thing. Set up a coordinate.
Oh, set up a coordinate. Okay.
Like you could set Cartesian, but you need to choose the coordinate according to the symmetry of the problem, right? Your problem should demand a specific kind of coordinates, so that you need to choose. So set up a coordinate.
Okay.
Same step.
Then we can write to the Lagrangian.
Okay. Then step 2 is find the Lagrangian.
Yeah.
Right.
Yeah.
Find the L. That's the next step.
Then just to solve the differential equation.
No, write down Lagrange's equation, delta L by delta QK equals to ddt over delta L by delta QK dot. So at this step, whenever you write delta L by delta QK dot, it's already resolved in the specific coordinate. So that's actually another advantage of Lagrangian system, right? Lagrangian mechanical systems, that
yes,
it's automatically resolved. So then step 4 is solve the differential equation. So that's again the most difficult step, because Lagrangian mechanics doesn't say anything about solving the differential equations again. It doesn't help that much.
yes,
right? So, but one step was actually easier. Finding the forces is much more harder than finding the Lagrangian for conservative systems. So for many problems in physics, we deal with conservative systems. So finding Lagrangian is easier than finding individual forces. So that's why it makes things easier. Also, to change a coordinate in Newtonian mechanics, it's harder, because every time you need to write down Newton's law in terms of Cartesian coordinate, then you have to transform the coordinate and resolve in the specific coordinate. So that's difficulty, but that difficulty is reduced down in just writing down the Lagrange's equation in Lagrangian mechanics.
when constraint, when there is some constraints force in the system.
Yes, then that's why finding force is difficult, right?
Yeah.
You need to deal with more things than necessary.
Yes.
Okay, so how do you deal with the same thing in Hamiltonian mechanics? What's the first step?
Set up a coordinate
Set up a coordinate.
and to
What
find
do
the
I do?
Lagrangian. Find the
Yes,
Lagrangian.
you need to find the Lagrangian.
Yeah.
Then
Then writing the Hamilton's equations.
no, you need to find the Hamiltonian
Oh,
and
okay.
actually momentums and Hamiltonians.
Yes.
P's and H. Actually, that's a small step. So whenever you can find the momentum in terms of, so finding momentum in terms of q dots is not that difficult, because that's basically delta L by delta q dot equals to P. So that's not a problem, but inverting that relation may be a big problem sometimes. What I mean is, like, say you end up having this kind of equation: Px equals to mx dot plus my dot. So it's also simple, because probably the next equation will have py equals to mx dot minus my dot, like that. But it's also simple, but sometime, like, this inverting this relation and finding like y dot and x dot in terms of p's, that would be difficult. So inverting this relation might be difficult. So finding Hamiltonian might be difficult sometimes, but not always. Like in many systems we know those are simple. And then what do you do after that, finding Hamiltonian?
Write down the equation.
Write down Hamilton's equation, right?
Yes.
Which one?
Uh,
Actually,
it's actually the relation between Hamiltonian and Lagrangian and the coordinate.
no.
Okay.
That step is here. Find the p's and h.
Okay.
So now you need to write down the explicit Hamilton's equation of motion. That's what I'm talking to. Okay. So now sometimes we would still solve the differential equation, but sometimes integration may be easier. Solve the coupled differential equations, right? Coupled differential it's acting weirdly. Differential equations, sometimes just by integration. So that's one advantage. Actually, it has started to help us solving the differential equation itself, right? We saw that in pendulum problem. So what are the steps for Hamilton Jacobi now?
Now set up a coordinate, find the Lagrangian.
So yeah, so first few steps are same.
Yeah.
Set up a coordinate.
Yes, and age.
To no, actually, what I'm writing. Yeah, find h. That would be enough.
Okay.
Okay, then write down the definition of momentum.
Yes.
Substitute delta S by delta QK equals to P K in H. So you have to replace your Hamiltonian, like all the momentas in Hamiltonian in terms of delta S by delta QK. That's one step. Then you need to write down the Hamilton-Jacobi equation itself. Write down h plus delta s by delta t equals to 0. Then separate
yeah.
separate the partial differential equation, right?
Yes.
Then, so remember, when you do this step is actually the most difficult step in Hamilton-Jacobi, separating the partial differential equation. But whenever you have separated the differential equation successfully, you have already integrated half, like you have already found the half integral constants or integrated half of the system already. So that's why it helps solving the differential equation. So next use actually now you need to integrate, right? Integrate the individual pieces. What is the spelling of
To find
individual?
Q.
Individual. It is G.
VIDUL. D.
UL. Okay. DUAL. Individual
Q.
pieces.
Pieces.
No, not Q. It's pieces. What is the spelling of piece? PIC.
Yes. Yes. That's right.
So then you get recollect collect the pieces and construct S. Sometimes you actually do not need to perform the integration explicitly. May not